The part that I mentioned, that the row space and the column space, yeah? Row space and the column space of a matrix. Okay, so we have a matrix. So the matrix given as usual, A11, A12, A1N, A21, A22, A2N. Okay, what's the last one? AM1, AM2, AMN. B and M by N matrix. Okay, then the row vectors is this row. They are row vectors. Row vectors. So row vectors, call it R1. And there is a comma here because it's a vector. Okay, until you have Rm. This is the row vectors. And we have the column vectors. So for the row vectors and column vectors, they have to look like rows and columns. Okay, last time I said doesn't matter. You can do vertically or horizontally, right, for vectors, but particularly because the question is on row and column, you put the column. So I call it C1. So A11, A21 until Cn. A1n, A2n, AMN. Just copy, paste. Okay. Now what is the row space and column space? So row space is the span of all the rows. This is the row space, the span of all the rows. So you take one row, two row, three row, you take the spanning set. And the column space is the span of all column. Okay, so that is the definition, the row space and the column space. Example. Example. I don't want to take the first example because it's 3 by 3. I want to take the different example. Let me see. Example 3.33. Okay. This is the matrix. 1, -2, 0, 0, 3, 2, -5, -3, -2, 6, 0, 5, 15, then 0, 2, 6, 18, 8, 6. Okay. The question did not give this. The question give you the rows, right? But I rewrite to match the definition earlier to have a matrix. The question is, find a basis. Okay, I changed the question. Find the row space and the column space. All right. Okay. So what you will do is, if you want to span Okay, once okay, let me think. Okay, this is exactly like the spanning set that you learned before, right? The spanning set that you learned before. That one is you are given some vectors, check whether it span this, right? And find the spanning, find the span. It's very similar, just they change into putting it as a matrix and then taking it as a row or taking it as column. So the row vectors are 4 vectors and the column vectors will be 1, 2, 3, 4, 5 vectors. This can be changed to another question like previous section in which your S has 4 vectors, find span S, right? Or the set S has 1, 2, 3, 4, 5 vectors and find span S. So this is 4 by 5, right? Okay. So we want to find the row space and the column space. And then you find the basis. That is the common question. Find the row space and the column space, or find the span of the rows or span of the columns and find a basis for that space. Okay. So you will write the row space or the set, the row vectors or the row space is the span of 1, -2, 0, 0, 3, 2, -5, -3, -2, 6, 0, 5, 15, 10, 0, and last one, 2, 6, 18, 8, 6. Okay, now this is 1, 2, 3, 4, 5, but there are only 4. This is a subset of R5. Okay, this is a subset of R5, but you only have 1, 2, 3, 4. So definitely the span set is not R5. It cannot span R5. Yeah. And whether they are the basis, you have to see whether they are linearly independent or not, or they are linear combination of the others, or they, but we do this by the row operation. Okay, I will not do the row operation because it is in the notes, or you can try yourself and finish. You don't have the notes, but I will give you the answer. 1, -2, 0, 0, 3, 0, 1, 3, 2, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0. I did not change the row, yeah? So this is one thing that you don't want to do, change rows, because your basis will change, okay? And do the rest of the operation. No changing of rows, except for the last one, because the last one, I want the third row to be down, the 0, except to the last one is okay. So what does it mean? Look at the final one. Okay, that means there is one row of 0 that we can exclude from the beginning. There's no use. Ada satu lebih. Okay, we just need actually 3. So if you do like this, then this is the same as the spanning of only 3. 1, 2, 3. So this is the basis, this 3, you put, copy paste, is a basis. of the row space. Call it A, yeah? U1, U2, U3, copy, paste. Okay, so the calculation is just reduce until row echelon form. It doesn't have to be row reduced echelon form. Okay, as long as you go to row echelon form, and you know it's row echelon because there's 1 zeros, 1 zeros, 1 zeros. And then you take the non-zero row, right? You take the non-zero row. So only 3. So this is the basis of the row space. The spanning 3. 3 give you like, I cannot say R5 is not 3-dimension, right? So if you really want to see the equation, you remember last time we put x1, x2, x3, x4, right? You try again, you put x1, x2, x3, x4, and then you will get the equation here, right? In x1, x2, x3, x4, then you will know exactly what is the spanning set. My question just now is to find a basis. So I did not do x1, x2, x3, x4. If you do this, you will get equation with all the x's, and that is actually the span, okay? In terms of x1, x2, x3, x4. Try that. Try that. So your answer will be, in that sense, you will write the row space is equal to, tak nak padam, P or that. What? You will write like this, is equal to x1, x2, x3, x4, 1, 2, 3, 4. But this one until you want 5, right? Oh, that one is for the, okay. That one is for the column space, sorry about that. This one you just leave like this. Because you don't need, for this one is actually the column space because we write as column. I will do that next. So for row space, this is your answer. For row space, you just reduce and then take the non-zero rows. That's it for the row space. Now we do for the column space, yeah? So for the column space, you take the span of column. Okay. Column 1, 2, 0, 2, negative 2, negative 5, 5, 6, 0, negative 3, 15, 18, 0, negative 2, 10, 8, 3, 6, 0, 6. 1, 2, 3, 4, 5. 1, 2, 0, 2, negative 5, 4, 6, 0, 0. 1, 2, 3, 4, 5. This is in R4. So definitely it's not the basis of anything. Okay. So you know that you have to exclude at least 1, maybe 2. Okay. But surely it has to be more than 2. Why? Because surely 2 is not a multiple of the other one, right? Okay. Saya bagi contoh ya, kenapa saya tahu mesti at least 2. Look at this. Look at this. This is another question. You want to find the basis of this spanning set. Suppose this is the column of a matrix. 1, 2, 3, 4, 5. Okay, definitely this is a multiple, right? So if you take the span, it's on the line ke apa ke, right? So you don't need those because it's just a multiple of this. When you take linear combination, you will get that number. And you just look at these two. They are not multiple of the other one. So even if you reduce, panjang kerja, buat kerja panjang-panjang, you will get these two at the end. Okay, but if you think about it, you can use the theorem. If it's a multiple, it is linearly dependent together. So you just cross out, cannot be in the spanning set. It's the same thing. So the answer is just these two as a basis. Okay, and later on you find what is the spanning set. If I put this as, say like this, lagilah zero vector kan? You don't need that in the spanning set. Cross. Only one. It can be only one. If I put this like 3, tadi 1 right? If I put this like this, still buang yang ni, cross cross. And you have this 1, 2, 3. 1, 2, 3. Then you can see that it's not any linear combination because it's only give this one to here. You won't get a linear combination. So turunkan pun you get this 3. So this is the basis. Okay. Suppose I get another one and this becomes like this. Apaan? One here, one here. And try. This now is 4. You can find the determinant. If the determinant is not 0, it becomes the basis, right? The answer is unique and so on. So this 1, 2, 3, 4. And this is actually a basis for the whole R4 because it's 4. Then you put equal to R4. I give you different kind of question to see with one same number of 1, 2, 3, 4, 5 vectors in R4 as a column, you can have the answer to be just 1. You can have 2, you can have 3, you can have 4, but definitely not more than 4 because the maximum is 4. Okay, so it depends on the question. And this can be done by just one same step, reduce. Saya tak tunjuk lagi macam mana, but I'm just showing you the possible answers. They can be span the whole R4 if you have enough 4 that is linearly independent. If not, you will have like 3, 2, 1. Okay, how do we get this? Okay, tadi pakai tengok je kan? Okay, now we go back. It's not easy, right? 1, 2, 3, 4, 5. Tenung mana nak nampak? Renung lama-lama pun you cannot see it's a combination kan? Tengok apa ni, siapa tu nama dia? Nabila Huda, dah berkerut-kerut dah nampak. Macam tu kan? Macam mana nak nampak? Memanglah tak nampak. Because I want to give you the answer. Okay, so what we do is we transpose and then we reduce. Transpose and then reduce. Just now we just reduce, right? So we transpose this, it becomes pukul 11, sekarang dah habis. Belum. Iya, saya pergi hari tu. Student penuh pukul 11:30. So if you reduce, then you take the row, it become R4. Then you convert again transpose, you will get column. So this is what you do for the column space. The reduce is just the normal reduce, yeah? Okay. Okay. So in the notes, I did not ask for the column space, but we will do this. Okay. Right. So 1, 2, 0, 2. Okay. 2 row 1 plus row 2. 0, negative 1, 5, 10. Okay, then copy. So let me save one step because I want to do this and this, but these two can be done together also to get a quick one. Okay, I will do negative row 2 plus row 3. And then negative 3 row 1 plus row 5. So I use row 1. So row 1 stays to change row 2 and row 5. Okay. And I stay row 2. Sebenarnya tak perlu kan? Confused lah nanti. But it's okay. Because I already get a 1 here. So tak payah lah ya. Still confused. So, balik semula. Reverse. I just change this and this. Tadi saya ingatkan nak jadikan dia satu tapi dah ada. Okay, so negative 3 row 1 plus row 5. Negative 3 and add. Oh, cantik. Okay. Okay. Next is negative row 2. Saya nak mengelak ni. Ya, salin dulu. Copy ke sini. Saya nak mengelak sikit. So, I change negative row 2 kat sini. Tak payah salin. Okay. 1, negative 5, negative 10. Faham Ada yang marah. Okay. Saya tak nampak. So, this is actually negative row 2. Okay, now I can do this. I can make this 0. 3 row 2 plus row 3. 2 row 2 plus row 4. Okay, to make this 0, this 0. Okay, 0, 3, and add. 3, and add. Right? 0, 2, and add. 2 and add. 2, negative 20, and add. Okay, and then, two more. Okay, 2 more. Negative 1 over 12. Row 3. Negative 1 over 12. Row 3. Okay? Dah? Dah? Okay. Tak cukup tu, dinding. 1. Yeah? Okay. Next is 12. Row 3 plus row 4. 12, row 3 plus row 4. Nak jadikan ni kosong kan? Okay. This is already row echelon matrix. So you take only the first 3. you take only the first three because that's the non-zero rows, which is originally the column. Okay, so you take 1, 2, 3. So when you write, when you write the answer, this you can write as the first three. Which is also this first three. Okay, so actually your answer is not unique. Okay, in the book, they ask you to find a basis for the row space or the column space from the original rows or columns of the matrix. So if the question is from the original rows or column, you will use this. If the question just to find a basis, you can use from the reduced one. And since for row operation, for row echelon matrix is not unique, then maybe your friend will get a different answer. Yeah, because I did not say that it has to be row echelon form. If you leave this as 2, and this is like this, and this is like this is also a basis. So it doesn't have to be 1, 1, 1. But we always reduce until row echelon because it will be easier, right? To make it the rest 0 and so forth. So you might see another different answer. As long as you can reduce, upper triangular is also okay, but it's not really an square matrix, right? So just reduce, because sometimes you get fraction, you don't want to get fraction. So you don't reduce until you leave it. Like probably you will have something like this. Maybe, right? You don't want to divide by 2 because you don't want 3/2, for example. But it's a multiple of your basis. So you can just write this as your answer. Paham tak? Yeah, understand what I'm trying to explain? That the answer is not unique and you need to reduce until you get some kind of, nak kata apa triangle pun, it's not necessarily a square matrix, but you reduce until you get all this. This means they're linear combination actually. That means you can write this probably as a linear combination of these 3. You can write this as a linear combination of these 3. That's why you can just get rid of those 2. So the basis is actually only 3. And this is not the whole R4 because only 3, right? So if you want to draw, this is R4. This is span S. When S is your column space. It does not span the whole thing because there is only 3 here. Okay, it is not the whole thing. Span S, S is here. This is S. Okay. If you have 4, which is linearly independent, 4 in S, I don't want to put here because 1, 2, 3, 4. Span S is the whole R4. Okay. If you want to see geometrically, I need to use R3, right? If it's the whole R3, X, Y, Z. for the whole R3, okay, for the whole R3, to have a basis of R3, you need at least 3 bases in S, right? So if you have like 3 vectors like this, if you have S inside R3, and then you have U1, U2, U3, linearly independent, then it will span the whole of R3. So the span S is R3. Then it will span the whole of the 3 dimension. Now, what if you have only 2? What if you have only 2? Say S is only, okay, the first one S, call it maybe this, right? This is our standard basis. Now, suppose your S prime, you have only 2. This actually will span, when you put X, Y, Z, you will get the, but this is a plane. This is just a plane. So if you draw, just now you have 3. So you will have X, Y, Z, and the vector is here, here, and here. So this enough 3, it will span the whole one. Even if you put S equals 4, and 3 of them are already, the determinant is not 0, already a basis. It's not linearly independent because it's 4, but it's span, right? 3 already span, at 4, at 5, at 6 already span, but not a basis because too much. So you just delete the rest. But if you have only 2, span S is not R3, not enough. This is just a plane. So span S is just a subset of R3. Only 2, yeah? Maybe we get only this and this. This is just this wall. Just this wall. Just this wall. Okay? Otherwise, it's 3 dimension. Now, what if there is only 1? Suppose we have only 1. It might be linearly independent, but it does not span the whole of the R3 because it's not enough. So this only span one line, right? X0, 0, that is one line. X0, 0 is just this line. Okay, just that line. This is a span. So this is an example of a basis of a span S, which is not the whole of the V. Okay, you can have 1, you can have 2, you can have 3. But if your original matrix gives you 4, even 4 rows, you need to reduce until you get less. It has to be less than that, okay, or equal to. I know if it is more than the dimension, like 7 by 3, right? And then you reduce, you get 3 by 7. Of course, you have to get rid of so many. Maybe 7 minus 3, maybe 4 or more. So this is the row space on column space of a matrix. So what you need to do is, for the matrix, write out the column vectors, right? And then reduce. For the column space, you need to write out the column as vectors, transpose, right? And then reduce. So you transpose the whole matrix, reduce. So the word is elementary row operation. Okay, any question on this? I think this is covering the row space and the column space. And type of question, we'll see more. You can try the exercise at the end. If I miss anything else, let me see. Okay, so we have another question. And okay, the last is the rank. The rank is the number of vectors in the basis. So if what is the rank of this? This is already a basis. So the rank is 1, 2, 3. So once you get the whole row and then you reduce what's left, the number of vectors is equal to the rank, right? We've seen this before. So this is rank 1, this is rank 2, this is rank 3. Just now when we got this, we got 3 answers, right? The 3, the rank is 3. When we do this, we also get 3 as the answer. So the rank is also 3. Okay. Oh, okay. There's a one little part for the, before we go to orthogonal and orthonormal, there's a null space of a matrix. So the null space of a matrix. What is the null space of a matrix? So you have a matrix, say AV is X. AV is X. AV. Okay, so let A, B, and M by N matrix. So this is a system of linear equation. From the system of linear equation, you will get AV is B, right? But for the null matrix, you equal to 0. So this gives us the homogeneous system of linear equation because this is 0. Solving this will give the null space. So V is in the null space of A. That's the definition of a null space. So the null space is the solution vector of AV equal 0. All right. So back to the chapter 2, system of linear equation. How do you solve V such that AV is 0? So you put all zeros at the end and you solve for V. All right. So let's go to one very simple A before we take a break. A is 1, 0, 2, 2, 1, 3. Given A is this, find the null space of A. Okay. All right, so the null space of A is V in R. This is 2 by 3. So this is in R3. Yeah, the 3. Such that AV is 0. Okay, so for this one. Because this is M by, oops, 2 by 3. Of course, this is 3 by 1, right? So this is has to be the 3. Okay, so how do you do it? 1, 0, 2, 0, 2, 1, 3, 0. So the V, if you put as X, Y, Z, this is actually here, right? The little X, Y, Z. Okay, reduce. 1, 0, 2, negative 2 R1 plus R2, 0, 1, negative 1, 0. Okay, then you want to write your answer. So x plus 2z is 0, y minus z is 0. So you remember we have the leading one, so x and y is not free, z is free, z is k, so x is negative 2k, y is k, z is k. Now your v here is equal to negative 2k, k, k in R. Then you put into the answer, okay, as your answer. Erase here, okay. Don't forget, you have to write your answer. So you will write negative 2k, k, in R. If you use different, negative 2x, x in R, it's okay. Yeah. As long as you put, this is actually the span of negative 2, 1, 1. If you put it melintang, R3 is okay in this case. As long as I know you meant for R3. How do I get this? I let k equals 1. If k equals 1, I get negative 2, 1, 1. So there's only one actually in the basis of the null space. So the question might be, find later on in chapter 4, they ask you the nullity. Nullity is the dimension of the null space. Oops. Later on, we call it NT, but here we just put null space, which is the rank of the basis. This is later we will use this, but the rank is 1 because there's only one vector. Okay, there's nothing new in this section. So I just conclude for this row space and column space. You will be given a matrix. The rows will be all the vectors in the row space, and the column will be the row column vectors in the column space. To find the row space and the column space, you need, for the row space, you just reduce and take the non-zero rows. Yeah. For the column space, you have to transpose first, reduce, and then take the non-zero rows, transpose again to get in the form of column. And the null space is solving the homogeneous equation. And once you get the answer, you write in the form of what is actually the vector in the null space. So this is pretty much all of those. Get the orthogonal and orthonormal set, yeah? Orthogonal and orthonormal set. You've seen orthogonal matrix, right? When you multiply, so this is just that. Okay, so let S be U1, U2, UN be a set in a vector space V. And we restrict only to Rn. Okay, there's no matrix, there's no function, there's no polynomial. So for this section, this is only for the vector space Rn. Then S is an orthogonal set if u dot ui dot uj is 0 for all I j equal 1 to n, I not equal to j. Ui, uj is any two. U1 dot u2 or u1 so forth. For all, yeah? For all, ij from 1 until n, but they cannot be equal. Okay, you don't dot together. This is a dot product, yeah? So if u is x1, x2, xn, v is y1, y2, yn, then u dot v is x1, y1 plus x2, y2 plus xn, yn. Dot product. That's why we want this equal to 0 as the number 0. Okay, so this is the orthogonal. And S is an orthonormal set if it is orthogonal. And the norm of ui is 1 for all I1 until n. The norm that you know from before, if u is x1, x2 until xn, then the norm of u is square root x1 squared plus x2 squared plus xn squared. So you see, with this definition, the standard basis is an orthonormal basis. The standard basis for Rn is an orthonormal basis. How do you prove that? Yeah? Example. Is an orthonormal, not only set, it's a basis. So if the question show that this is an orthonormal basis of R2, you have to show it is a basis, it's span, linearly independent, and you have to show it is orthonormal. Okay, so read your question very carefully. So I am not going to show it is a basis because we have shown this before, or you can show by the determinant it's not 0, right? So it's span and then it's linearly independent. So to show it is an orthonormal set, so let U1 is 1, 0, U2 is 0, 1. There is only 2, so you only have to dot product 2. U1 dot U2 is 1, 0 dot 0, 1. 1 times 0 plus 0 times 1, 0 plus 0 equals 0. Then you will ask, can I go from here direct to here? Because I do it in my head. If the mark is maybe only 2 marks, for the M1 and for the answer, you probably get a full mark if your answer is right. If somehow you do it in your head, no method, and then your answer is wrong, then you will get 0 mark. Tak ada markah kesian because your answer is wrong and I don't know whether you do the miscalculation. If you somehow write this, but you get suddenly 10, but these are all right, you probably get the marks for the method. So the moral of the story, just write out. Yeah. And you check for U1. This is square root 1 squared plus 0 squared, right? Which is 1 plus 0 is 1. Then you have to check for U2. 0 squared plus 1 squared. 0 plus 1 is 1. So S is an orthonormal basis, right? Some of the set, they are orthogonal but not orthonormal. Okay, for example, S prime 2, 0, 0, 3. Right, this is a basis. Okay, this is orthogonal. Okay, this is not orthonormal because square root of 4 is 2 and U2 is 3. Okay, so this is orthogonal but not orthonormal. So you have to put not equal to 1, not equal to 1. Okay, so S prime is orthogonal but not orthonormal. Because this is 0 is orthogonal, this is not 1 is okay. So how do we make this set if it is not orthogonal to be orthogonal? If it is not orthonormal to be orthonormal? Okay, to make orthogonal set to be orthonormal is easy. You just divide by the norm. Okay, so I claim if you have a U, you divide by the norm. Okay, this actually is equal to 1. This is actually equal to 1. So, for example, this one, yeah? U is 2, 0. The norm is 2. So you divide U by the norm. Or you can write like this. The norm is 2. And you get 1, 0. Then you can get the norm equals 1, right? And this one, the norm is 3, you divide by 3. Then you will get 0, 1. Okay, so this is how you make it orthonormal. Because basis is just a spanning, you can just do the multiple. It still span the same set. It's not the same set as, but it span the spanning, the whole basis is still the same spanning set. Okay, so how do you show this? This is a theorem actually, yeah. Proof. The norm of the number is just the number. The number is just the number, right? And then the norm of U. That's the proof. It's just take the norm, divide by the norm. It's just one. Okay, senang kacang. Saya boleh tanya dalam final, dalam quiz. Proof is equal to 1. Tu pun nak tanya nanti deh. Okay, tak apa. Okay, so you have example and calculate the norm, theorem 3.15. Okay. Now, I already mentioned about orthogonal basis and orthonormal basis. Okay, now we are ready to go to Gram-Schmidt process. So you will have your S. A basis or a set. We will use this as the orthogonal set. We use this. As the normal set. Okay, so to go from orthogonal to orthonormal, you just divide by the norm. It's as easy, right? How do we go from the original? Suppose we take that as a basis already, yeah, of the span S. Okay, don't put in all the extras, meaning we reduce first, then we take the non-zero rows. All right, so suppose we have that. Now what's the formula? If the book give you UVW, it's okay, it's just the same thing. Okay, so let me do consistent, yeah. UVW, okay. Dekat sama V ya. W. Okay. So the first one, V1 is U1. V1 is U1. Copy paste. If you copy, you paste the wrong V1, you will lose the whole of the rest of the answer. Copy pun tak betul. Okay. Now for the next one, V2. V2 is U2 minus U2 dot V1, V1 dot V1, V1. Okay. Now this is dot product, is a number. This is also dot product, is a number. Multiplied by a vector, so it's a vector. U2 minus a vector is a vector. Okay, you call it V2. Now V3, take U3 minus this U3 dot V1 over V1 dot V1 V1 minus U3 dot V2 V2 dot V2 V2. So imagine if your V2 is wrong, you need to use this V2 again. So if your V2 is wrong, this is also wrong. So this is just a computation, but you really need to be careful, yeah? Okay, so let's see one example. S equal 1, 1, 1. 0, 1, 1, 0, 0, 1. So this is in R3 because you have 1, 2, 3. If you see, this determinant, right? Determinant is 1. Okay, so this is a basis. It's a basis of R3. So we want to find, let S be this, a basis. Then the first question, show it is not orthogonal. Show it is not orthogonal. If you have to show it is orthogonal, you have to show every pair. Every pair is orthogonal. If you want to show it is not orthogonal, just take one pair. No need to show all. So this is not orthogonal. Claim S is not orthogonal since, so let this U1, U2, U3, yeah? U1 dot U3. Why U1 dot U3 not U1 dot U2? Because U3 is easier to multiply. 1, 1, 1 dot 0, 0, 1 is equal to 1 times 0 plus 1 times 0 plus 1 times 1 equals 1, which is not 0. Ni ada markah tau ni? Because it is not 0. Okay. Or you can use any other pair. They are all not orthogonal. Alright. Ni bukan part of the soalannya, saya just checking. Alright. The question is, transform S into an orthonormal basis. Itu soalan dia. Okay. Now, let S prime be V1, V2, V3 and orthogonal basis. Okay. Then, using Gram-Schmidt process, V1 is U1, copy. Copy je. Okay. V2. V2 is U2 minus U2 dot V1 over V1 dot V1, V1. Actually, V1 is U1, so, but we just put V here because later on it's all V, yeah? So, copy 1, 1, 1 minus 1, 1, 1 dot, hey, who said 1, 1, 1? V, U2, 0, 1, 1 minus 0, 1, 1 dot 1, 1, 1 over 1, 1, 1 dot 1, 1, 1 multiplied by 1, 1, 1. Copy je, tak ada buat apa-apa. U2 is this minus U2 dot this over the norm multiplied by this. So, two, yeah? 0 plus 1 is 2 over 1 plus 1 was 1 is 3. The calculation is easy, but normally it includes fraction. So you have to be very careful. Okay? And if you make something careless mistake, you will do careless and you will bring this until the end. Markah banyak ni, eh? And it's easy to score. So 0 minus 2 over 3. 1 minus 2 over 3. 1 minus 2 over 3. Okay? Okay ke tak? Okay, you had to use, terlupa dah. Minggu keberapa ni? Okay, that's the magic word, right? Okay, so this is V2. You can check your answer and you can get 100% very easily. Check your answer means you can check V1 dot V2 and definitely you have to get this equal to 0. So multiply negative 2/3 plus 1/3 plus 1/3, right? This is it. Check, saya suka ada check kat situ. I want to give a hat, bagi topi, to the V2 because I don't really like fraction. Okay, I don't want to use this in the next one. So let V2 hat, because basis can be a multiple, right? I multiply all by 3. I get negative 2, 1, 1. Okay, I get rid of this. Nak nombor besar, darablah 30. Suka hati nak besar-besar. Okay, this is the LCM, right? Okay. So you can still check that these two is still orthogonal. Jangan salah darab pula. Now I have to find V3. Okay? Okay. So V3 is U3 minus U3 dot V1 over V1 dot V1, V1 minus U3 dot V2, V2 dot V2, V2. Which is U3 here, 0, 0, 1 minus 0, 0, 1 dot 1, 1, 1 just now over 1, 1, 1 dot 1, 1, 1 multiplied by 1, 1, 1 minus U3 0, 0, 1 dot negative 2, 1, 1 negative 2, 1, 1 dot negative 2, 1, 1 then negative 2, 1, 1. Zero, 0, 1 minus 1 over 3, 1, 1, 1 minus 0, 0, 1 over 6. So 0, 0, 1 minus 1/3, 1/3, 1/3 minus 1/3 negative 1, 6, 1, 6. And this is equal to 0 minus 1/3 plus 1/3. 0. 0 minus 1/3 minus 1/6. 3 over 6 minus 1 over 6 is 2 over 6. 0 minus 1 over 3 minus 1 over 3 minus 1 over 6 minus 3 over 6 minus 4 over 6. Kira. Over 6, yeah? Answer? And then last, 1 minus 1 over 3 is 2 over 3 minus 1 over 6. So we can multiply this 4, 6. Okay, this is You can use your calculator. Okay. So this is V3. So V3 hat is 0, -1, 1. Then you can check this with V2 just now. Okay. And you get your S prime. So this is 1, 1, 1, -2, 1, 1, 0, -1, 1. You can check your answer. Multiply these two, you get -2 plus 2 plus 2, 0. Multiply these two, -1 plus 1, 0. Multiply this, -1 plus 1, 0. So this is orthogonal. You will have to get the orthonormal. Okay. Padam ya? Okay, so this, the square root 1 plus 1 plus 1 is square root 3, right? So you divide. This is square root 6. And this is square root 2. Orthonormal. Imagine if I have 4 vectors, then you have to do it once more. U4, right? Then you continue. U4, V4 equals U4 minus U4 dot V1 over V1, V1, V1 minus U4 dot V2 over V2 times V2, V2 minus U4 dot V3 over V3 times V3, V3. I won't ask you question more than 4. 4 pun, ini pun, whew. And be very careful with your fraction. Okay, it's very easy to score this question, but it's very easy also to do careless mistake. Okay, so I am done with this chapter. Whew. It's a very long chapter, and you can now do all questions for this chapter. Okay, and the question for the row space starts with number 49. Basis for row space, dimension of row space, column space, and then there's a null space, and then Gram-Schmidt start from 52. Shiham, can you help me share the question? I'll give some hints.
Okay.
Yeah, the question in the back. Number 52. So next week on Sunday, I already put in the Google Calendar. On Sunday, 5th of June, that our class will be in DK2, yeah, C17, just across the mosque. Okay, DK2, C17. Okay, so number 50, apa tadi? Saya kata dah lupa pula. 52, ya? Okay. Apply Gram-Schmidt process to the given vectors to obtain orthonormal basis for R2. So 1, 2, and 1, 3 is a basis. because the determinant is zero. The determinant is 1, which is not 0, so it's a basis. So you just do Gram-Schmidt. The other one also. 53. Okay, apply Gram-Schmidt to obtain orthonormal basis for R3. So you have to check first. 1, 0, 1, 1, 1, 5, 2, 2, 1. Syihan boleh je nak conteng kat situ kalau nak conteng lah. The determinant, yeah? The determinant is 1 plus 2, 3, minus 2, 1, minus 10, minus 9. So, okay. So, you do Gram-Schmidt. B, 1, 1, 1, 0, 1, negative 1, 1, 2, 1. So, the determinant is 1, minus 1, 0, minus 1, minus 2, 2, 3. Okay, determinant also 0, not 0. So it's a basis, you just apply Gram-Schmidt. But for 53C, 53C, when you see this, you write as a column vector 1, 0, 1, 1, 1, 1, 2, 2, 1, and 1, 1, 3. You want to find, you want to obtain an orthonormal basis. So this is more than 3. You need to get rid of 1. So you can reduce and take which one that you want to. There are 2 ways actually to find this. If you reduce and you get rid, you can take the leading one. Okay, because we start with the vectors as column, yeah. You reduce and then whatever is left, you take which column. So I do like this, negative row 1 plus row 3. Boleh stop sharing sekejap kalau tak nampak. Negative 0, 0, negative 1, 2, yeah. Right? Negative row 1 plus row 3, 0, 0, negative 1, 2. Okay, this can be the leading one. Okay, you can just take these 3 as the basis. Okay, so you can start your S, the original, yeah? Take the original. 1, 0, 1, 1, 1, 1, 2, 2, 1. You can double check that the determinant is not 0. This is how you get rid of the extra. If you want to do row, like the row space, it's different, yeah? If you want to do row, you will do like this. 1, 0, 1, 1, 1, 1, 2, 2, 1, 1, 1, 3. Then you reduce. This is as row, yeah? 1, 0, 1, negative row 1 plus, ini susah sikit, row 2. 0, 1, 0, and negative 2, row 1 plus row 3, 0, 2, 0, 0, negative 2, row 1 plus row 4, ni apa ni? Salah. Negative 2 and add, negative 2 and add, negative 2 and add. Okay. 0, negative, negative. Then one more, 1, 0, 1, 0, 1, 0. Negative 2, row 2 plus row 3, negative row 2 plus 0, negative 2, 0, negative 1, 0, 0, 2. And then one more, you will get this 0. So you take the first 3. Take the first 3 means you take the first 3. Take the first 3 means these three. So you can see the difference from the beginning as whether you want to write as column, choose the column with the leading one, make that column as your set, or you write as row, choose the row that is not zero, take the original row, put in the set. This is the difference. This is something to do with row and column space. Once you get into 3, you can use Gram-Schmidt. Ni hint je tau, bukan bagi jawapan. Okay. Shiham, share again. So this is for that. If you have more than enough, go to the next question. Okay, number 54, R4, yeah? So you all still have to check, yeah? You still have to check 54A, whether it is a basis or not. So let's see if you can do 1, 1, 1, 1, 1, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 1. You know, when you add these two, you get this, right? When you add these two, stop sekejap, dah salin soalan. When you add these two, you get this. So definitely, this 3 is not in the basis. From these two, you can get this. So you can actually cross out this one. It's not linearly independent. This one, scrap out. And then this one definitely you cannot get from these two. Okay, but if you want to see why, you take this determinant here, right? And then you calculate determinant again, plus minus plus minus minus, then you get 0. So the determinant is 0. That is one way to see why it's not a basis. Once is because the determinant is 0. Once is I know by looking. U1 is actually U2 plus U3. So if I put U1 minus U2 minus U3 plus K, plus 0 times U4 equals 0. Yeah, because this is true. So I put U1, bring here, minus U2, minus U3. I need a U4, just multiply by 0. Is equal 0. This implies the C, right? C1 is 1, C2 is -1, C3 is -1. Not all equal to 0. So it's dependent. Okay. So what can we do? Dah lain pula soalannya. So I will try to get rid of this. So if you do this, 1, 1, 0, 0, 1, 0. Okay, just now I write as column, yeah? I take the original one as row. 1, 1, 1, 1, 1, 0, 1. Sama je kan? Oh tak. 0, 1, 0, 1, 0, 0, 0, 1. I write as row. Then I will choose the row which is not 0. Okay, so this is the first, the second, the third, the last one. So 1, 1, 1, 1 minus row 1 plus row 2, 0, -1, 0, -1. I got 0, 1, 0, 1, 0, 0, 0, 1. And I got 1, 1, 1, 1, 0, 1, 0, 1. I take negative row 2. ngelak sikit, but you can just add. Okay, from here, I can take this, this, and actually this. Dia tak sampai row echelon lah, but then if you tukar, nanti kena tukar yang original, right? So I just take that as my set ish. Okay. 1 1 1 1 1 0 1 0 0 0 0 1. Ini guna row guna row operation, because this cannot be both third at the same time. This plus this is this. Kalau ada satu je okay. I can have also tadi yang tadi tu, tadi by looking I can get this 3. If we do this, I can get this 1 2 3, the original 3. So it's a different S. Okay, and the answer is not unique as long as you get 3 which is not linearly dependent. I can have like this, but 1 1 1 1, the third one. And this is a subset of R4. Not the whole R4, it does not span R4. So when you have to find the orthonormal basis of this subspace of R4, you use this either one. So you will see whether I will give a question like this or not, because I will have different answers from many students kan. Pening kepala saya nak tanda, so banyak pilihan jawapan for this one. So this is to show that the original one is not the basis, reduced as a basis, and then Gram-Schmidt. Okay, next, I have 2 minutes, Shiham. Next, share the next question. Okay, number 55. So you have to find the plane defined by that. So you have to solve that equation. Okay, of course you will have 2 free variable. From those 2 free variable, you will get, take out K1, take out K2, you will get 2 vectors. That becomes 2 vectors, and then you find it orthonormal. Try dulu Then 56, you just reduce the homogeneous and solve. 57, to make it orthogonal, you multiply those 2 equals 0, and you solve. Easy. 58, the same thing. You want to do orthonormal, you have 2 equations and 2 unknowns. You have 2 unknowns. You multiply equals 0, dot equals 0 for orthogonal, and the individual one for y, the norm has to be 1. You get another equation, then you solve. Okay, 59, ada lagi? Habis dah? Alright guys. Okay, stop sharing. So that is the end of chapter 3, which is a very long chapter. And we will meet again on Sunday. One question, if any.